There we go. All right, so guys, if memory serves, we are here. Is that true? We talked about the idea that a precipitation reaction is a reaction where a precipitate forms. We said that precipitates are non-soluble substances that are created in solution. We then, I think we alluded to it, the idea that all precipitation reactions are double displacement reactions. Did we say that? And the idea is that we get that double trading of partners, and one of the things that forms is not soluble in water. Is that a good starting place for us? Are we good to there? Okay. So guys, with that said then, not surprisingly, this is then when we need to bring the solubility rules into this conversation. Now, Matthew asked the question a minute ago, do we need to worry about this, or can we just worry about table 4.1? And I probably said way too much about my thoughts on that. But guys, here's the thing you got to get. When you sit down to the AP test, there's only 7 free response questions on the AP test. They're long, but there's only 7. And so at some level, the purpose of these questions on the AP test is to give you the opportunity to represent general understandings and general skills. And so the chances of them coming after you and expecting you to know really obscure solubility rules are very, very thin. What you're going to find is that in homework, because this is wide open, in homework, you're going to run into some weird, oh gosh, I didn't even know that was a thing. Does it dissolve in water? But by the time you get to the tests and then to the AP test, because remember our unit tests are always old AP questions, you're going to find that it's much more, it's the usual suspects, bromine, chlorine, acetate, nitrate, sulfate, those sorts of things. So I wouldn't spend a lot of time chasing the minutia. I would focus on the big ones. So, guys, with that said, let's do table 4.1 together. Again, you were not to have simply rewritten it. You were to have summarized it. So, guys, grab your summaries of table 4.1. Grab something you can write with. And let's learn from each other. So guys, we're going to do this slowly so that people have the opportunity to jot down ideas. And I will start. If it's an acetate or if it's a nitrate, it dissolves in water. Can I get an amen? Y'all know that just means we agree. You did know that, right? Yeah. All right. So did y'all get that one? Okay, other summaries. You guys always come up with brilliant ways of distilling this stuff. I love hearing them. What were other things that you all included in your summaries? Good. Dissolved in water. And guys, realize that the minute you say always, if there's one exception, you just got proved wrong. Also an important lesson to learn when you get married, never say to your spouse, you always or never do something, because all they got to do is come up with one example of when they did or didn't, and they just made you out to be a liar. So when we say it always dissolves, there's probably exceptions, but it's close enough for us. So guys, what else? So we've got 3, acetate, nitrate, and ammonium. Go ahead. And could we maybe expand that? And could we say all group 1 metal salts? That's what I did with it, Chandler. And do you guys have any, I don't remember table 4.1 by word. Is that supported in 4.1? Okay, so the alkali metals, the group 1 salts, all dissolve in water. Ronnie? Well, so francium or francium, depending on how you say it, typically doesn't fit into a lot of the trends simply because it's very radioactive, and it's so unstable that we typically don't do chemistry with it. I don't have any Francium salts next door. I know. I do, however, have a human fetus. Depends on how radioactive it is. So guys, other generalizations. Let's stay on point here. By the way, the fetus is going away today. Say that again? Well, so I learned about what happened. We used to have a collection of human fetuses that went, seriously, it went from like 1 month to probably that guy, like 8 months. And every month we had an example of fetal development. This was back in the Wild West days, like when I started teaching, when teachers could do anything they wanted and not get in trouble. And it was, all right, I'll tell you the story. And so it turns out that we had a whole set of fetuses. And then when we moved into the new building, Mr. Maurer actually only kept one of them, that one. I don't know what happened to the others. And it got hidden in a closet somewhere. And Miss Harward found it, worked for 2 years to get rid of it, finally got sick of it, and dropped in on me. So now it's up to me to get rid of it. And actually it was really cool. I called the University of Utah and their cadaver lab coordinator up there. It was really weird. He's like, yeah, we'd be happy to take it from you. And I'm like, really? I don't know who it is. I have no backstory. I don't know what's going on. And his response to me was, we get these calls all the time. I said, you have people? Yeah, that's I was like, okay, this is sick. And apparently there was a day when doctors would deliver stillborn and like take them home and show their kids. Yeah, it's like, and the guy's like, yeah, and sometimes people will miscarry at home and just keep it. And then they're like, we don't know what to do, so I get these. So anyway, the U is going to take it and cremate it and bury it. But then I'm like, how do I get it to you? And the guy was like, call BYU. The people from their cadaver lab are coming up in a couple days to get cadavers for the year. Call them and see. And the guys at BYU were awesome. They're like, yeah, we'd be happy to transport. So they're coming by at noon to transport this thing. It was really cool. So anyway, that's my fetus story. So guys, back to the solubility rules. So let's talk. So we've got acetates, nitrates, ammonium, and alkali metal salts all dissolve in water. What else? Go ahead, Ryan. So let me tell you how I remember this. And it could be wrong or it could be too narrow. But the thing that I remember now goes to the strong bases. Because the strong bases are hydroxide salts. And I know that calcium, strontium, and barium hydroxide do dissolve in water, but magnesium and beryllium hydroxide do not. So is there something that says that all of the group 2 salts dissolve? Okay, and there's the heavy. And the way that I do that mentally in my brain is I draw a horizontal line across here, and heavy is everything from there down. Okay, but I like the idea. What else, y'all? Yeah? So this line does not extend to the first group. So it's all of the alkali metals and the heavy alkaline earth metals. So all of group 1, heavy group 2. What else, you guys? Yeah? Yep. Yes. With silver, mercury plus 2. Correct. And so, guys, this is what yes. I go, all of the halogens dissolve in water unless they're bonded to silver, lead, and mercury. Now, guys, the silver, lead, and mercury deal is +2 if it can be. So it's lead plus 2, mercury plus 2. Silver can't be plus 2. It only goes plus 1. Yeah. Well, lead only goes 2 or 4. But if it's 4, it dissolves. If it goes 2, it doesn't. And that's actually one they will hold your hand to on the test. They love that one. So guys, remember 2 is the magic number. Silver, lead, and mercury, that'll just come. Silver, lead, and mercury, but it's if it has a plus 2 charge if it can. So mercury plus 2, lead plus 2, silver can only be plus 1. You okay? What else, y'all? Other summaries? You okay? Let's call that a good working menu. And actually, Michele, I'll give you a copy of this as well, even though you're not in lab. Guys, the next lab that we're going to do, not the one we're doing today, but the next one we're going to do, I think it's lab 21, is actually a pant load of aqueous reactions. And you know how our labs have a discussion section up front? The discussion section of this lab has another retelling of a solubility table, and I like it even better. So when I share it with everybody, I'll get you one as well. And then we maybe even can add some other ideas to our summaries. Okay? All right. So guys, with that said, here's what you need to do. Find a place in your notes where you have, well, you need a clean sheet of paper. It could be the back. What we are about to do is going to take up an entire sheet of paper. So guys, we had a task yesterday, Wednesday in class, and I don't think we ever finalized it. What are we calling the video babe? The woman's voice in all of the videos we're going to watch. Rosalind? Oh. Rosalind. So, you're not going to find this surprising, but as a child, I actually looked just like Calvin. So, Rosalind. Okay, what about this? Who's Calvin's love interest? Is it Sally? Susie. Can we call her Susie? Would that because Rosalind is a little old school and it's hard to say. How about Susie? All right, this is Susie. Yes. All right, guys, we're going with Susie. I give you precipitation reactions. Let's make sure this is targeted right. So guys, just to get the juices flowing.
The first precipitate will be produced from aqueous silver.
Okay, stop. What we are doing in this first demonstration is we are mixing aqueous table salt and aqueous silver nitrate. Guys, if we didn't see these dissolved in water, how would we know that they both dissolve in water? What's the giveaway with table salt? Sodium's group 1, chloride's a halogen. It's got everything going for it, right? But guys, how do we know that silver nitrate dissolves in water? Because it has, be careful with silver. Silver's an exception. Nitrate always dissolves in water. Guys, silver's tricky. Follow the logic. Guys, when you see silver, you should have little alarms going off going, uh-oh, silver's trouble. Because silver is a rule exception, silver, lead, and mercury. When you see silver, you should get a little twitchy. So now, guys, let's talk. When these things go double displacement, what's going to precipitate? Silver. It's already silver nitrate. All right, let's look. Sodium goes with nitrate. Silver goes with chloride. So, guys, listen. This isn't. We need to sort of pull back and think. We know that all nitrates dissolve in water. Yes. Therefore, it does not matter what nitrate's bonded to, it will always dissolve in water. So you will never have a nitrate precipitate. Stop and let that sink in. You will never have a nitrate precipitate. So if it's not the nitrate, then it's got to be the silver chloride. But now, because we're starting to own these solubility rules, we go, all of the halogen salts dissolve in water except for silver, lead, and mercury. And it's at that point we've identified our precipitate. Do you get the idea? This is the thinking that you've got to be able to engage in, guys. So coming back then, clean this up. Here we go. Uh-oh. Come on, Susie.
The first precipitate will be produced from aqueous silver nitrate and aqueous sodium chloride. Aqueous sodium chloride is added to the silver nitrate solution. We observe a white precipitate of
Chandler, what did you call those last time? Chunks.
silver chloride.
Floaties.
This heavy precipitate thickens and falls to the bottom of the test tube as more aqueous sodium chloride is added to the silver nitrate solution.
Okay, we get the idea.
This is a white precipitate of silver chloride.
Okay. Guys, oh my gosh. So don't say anything, but what's your precipitate going to be? Don't say anything. So let's do this. What do we know that our precipitate is not? Nitrate. So if it ain't the nitrate, it ain't the sodium nitrate, right? They trade partners. Sodium to nitrate, nothing. So what now will be our precipitate? Silver iodide. You good? Okay. So guys, with that logic, here's what we're going to do. Do this on a clean sheet of paper, and I want you to do it big. So, reading along with me, 1 molar lead-2 nitrate, 0.5 molar potassium iodide solutions. So, guys, stop writing and listen. If you ran into this on the test, and if your brain froze and you forgot all of the solubility rules, how do you know that lead-2 nitrate dissolves in water? It has a molarity. Remember, your brain froze. You don't remember the solubility rules. Molarity is the amount of stuff dissolved. It's a concentration, right? If it's got a molarity, it dissolves in water. Similarly, potassium iodide, you don't need to know the solubility rules. It's got a molarity. So guys, here's what I need you to do. Please, across the top of your page, as wide as the page if you can, make it big, write the balanced equation for this reaction. So, guys, as you're doing this, Josh asked the question a couple days ago. He said, "What's up with these subscripts? These small S's and L's and stuff?" And we said that those are the subscripts that indicate phase, and that we would never need to use them in this class. Please use them now. Please put subscripts on the substances in this equation. You'll find it helpful as you're trying to learn what's going on here. You guys need another second? Okay. All right, so guys, let's gather up and let's talk about this. So we know that our reactants are lead-2 nitrate and potassium iodide. So lead-2 nitrate, trying to think of what this is going to look like. I'm going to do what I can to try to get this on one screen. It may not work, but I'm going to write, if I can, a little smaller with the hopes that I can do it. So lead, no, I don't like that color. So lead-2 nitrate. Do we need to talk? Lead is +2. Nitrate's -1. There you go. And potassium iodide. Double displacement reaction. Lead hooks up with iodine. Lead is +2. Iodine is -1. PbI2. And then the other product, the K, hooks up with the NO3. KNO3? Yeah.
Does it matter which product goes first?
It does not. Not at all. So now, guys, let's balance it. We've got 2 nitrates, so I need a 2. So I need a 2. Am I okay? Okay, now let's go back and let's do subscripts. How do I know that lead nitrate is aqueous? It has a molarity. So that's aqueous. Same thing with Ki. Now, guys, this is where your solubility rules have got to kick in. Which one of these two do you know for sure is aqueous? Nitrate. Now, guys, what about Ki? What are some of the solubility principles that we shared that might apply here? Okay, it's lead. So what's the big rule? All halogens dissolve in water unless they are bonded to silver, lead, or mercury. Which lead? +2. Uh-oh. That's our +2. So this is not aqueous, so what subscript does it get? S for solid. Okay, so now, guys, I'm not going to get this on one screen. So you have a huge advantage over me because you have a long page. I'm going to create a clean screen. Here's what you're going to do. Let me think. So we're going to go here. Come on. Here and here. Guys, please do this with me. As wide as your paper, please draw 3 beakers. Then put some water in them. Just make them big. Probably like a couple inches tall. Yeah. You could go half a page. It's not wrong. But, oh gosh. Guys, sorry. You wanted, my bad. You wanted to skip down. You know what? If you didn't, it's okay. If you did skip down a few lines and then draw these, that's great. If you just put it right below the balanced equation, that's okay too. So if you've got, if you've got this right there, that's fine. Either way works. So, guys, with that said, here's what I'd like you to do. Beneath the first beaker, please write lead-2 nitrate. Beneath the second beaker, please write, that's ugly, potassium iodide. And then beneath the third beaker, please write the word products. Now, I think you're going to be a lot happier if you do this in pencil. Does anybody need a pencil? You guys all working in pencil? Okay. So guys, here's what I'd like you to do, please. In the left-hand beaker, write the ions, better word, the substances that are floating around in that beaker when you make 1 molar lead nitrate. In the middle beaker, please write the substances that are floating around in a beaker of Ki, and then stop. And look, great question. When they started asking these questions on the AP test back in 2014, they forgot to tell students what to do about the water, and they had to invalidate all the questions. They will now tell you on the test. We are not. Let me show you what I'm talking about. Ready? Ki, strong, weak, or non-electrolyte. It is a soluble salt. All soluble salts, strong electrolytes. So guys, in a beaker Ki solution, there's Ki. What's in there? K and I. You know what? Shoot. I'm going to do this. I want to make this fit. At least this first line so you get this. So I'm going to go down here. You're okay. But I'm going to do this because I think this will make this a little easier to see. So, guys, for example, in this first beaker, or in the second beaker, there is no K. There's no Ki. There's potassium ions and iodide ions in solution. So guys, with that said, please in the left-hand beaker, write in what's floating around in that solution. If you do this right, you're going to have 3 things. Sometimes my board is just not the ideal space. So guys, what's over here in this first beaker? Got some PBs. So guys, what's wrong with this? Let me ask you this. If it was that, what would it look like? A lead sinker. Guys, PB is solid elemental lead. This does not dissolve in water. It sinks to the bottom of the lake and drags your power bait down there to catch fish. Guys, lead is not dissolved in water. Hang on, Spencer. This is lead 2+. And guys, that is actually the way to write that. When we're looking at ionic charges, it's number first. So it's lead 2+. So what else then is in solution? Nitrate. NO3, but there's 2 of them. Hang on just one. I see, I'll get you there in a second. So guys, now we've identified the ions that are in solution. You good? Spencer, go ahead. Like lead? You'll get it. It takes a little while, but you'll get it. So now, guys, let's do this. Let's together, because you've never done this before, let's now draw what's in the products beaker. Right? Can you picture this? Watch my hands. You had a beaker of lead 2 nitrate. You had a beaker of potassium iodide solution. You dump them together. Now that one beaker is your product beaker. The question is, what's in there? Well, guys, let's actually start on the right. So potassium nitrate dissolves in water, yes? Yes. It's aqueous. So what that means then, guys, is we've got 2 potassium nitrates in the products. But because this is aqueous, we've got a K, and we've got a K, and we've got an NO3, and we've got an NO3, and those dudes are all still floating around in water. Is that okay? But now, guys, what about the lead-2 iodide? It's a solid. And this is the accepted way to write this. PbI2, and draw a half circle over it to express that it is a solid sitting on the bottom of the beaker. You get the idea? You guys okay? Okay. So now, gang, look at what we're going to do. After today, you are never going to write chemical reactions the same ever again. Guys, this reaction that you wrote up here, you will never do again in this class. This is what is called a complete molecular formula. And while that used to be valuable to us because it showed us the overall picture of what was going on, guys, this is not the way we represent this chemistry. The way that we represent the chemistry is actually visually represented down here. So guys, check this out. If we have a beaker of lead-2 nitrate, are you guys all comfortable that we don't have any lead-2 nitrate in there? It's actually 1 lead and 2 nitrates. That's what we're going to write down. And guys, do this slowly with me. So in this, we actually have a lead 2 plus and 2 NO3 minuses. That is actually what is inside that beaker. Now guys, let me ask you a question, and this is to Josh's point. Here's the answer to your question. Why do we not need to put the aqueous subscript on the lead 2 plus and the nitrate minus 1? How do you know? Well, they are aqueous. How do we know that these are aqueous so that we don't have to put aqueous? Go ahead. So it is inferred because we understand that, but there's something else there that tells us. Nope. The charges. Guys, the only way that lead 2 plus can exist on its own is if it's dissolved in water. It can exist as lead 2 plus when it's bonded to lead 2 nitrate. That's a salt, it's a crystal. But guys, in order for lead 2 plus to exist on its own, it's got to be in water. The only way for nitrate ion to exist on its own, it's got to be in water. Water stabilizes it. So anytime you've got an ion by itself, it has to be dissolved in water. Okay? That, Josh, is why we don't put the subscripts on it. Okay. So now, guys, what about this? Now we need to represent what is in this beaker. Well, what do we have? Well, guys, it turns out we actually have 2 potassiums and 2 iodides. It should actually be this because, that should be negative. It should actually be that because of the balanced equation. So now we've got 2 K pluses and 2 I minuses. Do you see it? So now, guys, do this. On the right-hand side of this equation, please represent here what is in the beaker down below, just like we did with the others. I'm going to get this all on this screen. Yeah. You guys ready? Let's talk. Guys, don't miss this. Do I break the leads and the iodides apart? No. Why not? because it's not soluble. It doesn't dissolve in water. It doesn't ionize. The lead 2 iodide is sitting at the bottom of the beaker as a pile. This stuff is actually white. As a pile of white stuff, chunks, sitting on the bottom. But guys, what about the potassium and the nitrate ions? Are they together or are they separated as ions? Separated. So this then would be 2 potassium ions and 2 nitrate ions as I slowly run out of space. You guys good? Yeah. No. That was to Matthew's question as well. It doesn't matter the order you put them in. Yeah, Kaylee. Yeah, it doesn't matter. You guys good? Guys, this then is where this entire day was headed. Don't miss this. This is what is called a complete molecular equation. The one below it that you just wrote, the name will make sense. The one below it is what is called a complete Ionic equation. Do you get it? What's the difference? In a complete Ionic equation, you're breaking all of the strong electrolytes into their ions. Does that sit okay? Now, guys, check this out. We are now going to take the last step towards the goal. So here's what you do. Start on the left and work to the right. So guys, lead started out as this. Don't miss this. Lead started out as lead plus 2. Guys, in your mind's eye, what does that look like to be lead plus 2 in that beaker? What would you see? Nothing. But what is that lead? What is the experience of that lead plus 2? Well, that dude's dissolved in water, surrounded by water molecules, dissolved into solution, right? You get the idea? Here's the question. Where does lead end up? In a pile hooked up to iodine at the bottom of the beaker. So guys, here's the thought. Lead changed. Lead went from dissolved in water to piled up at the bottom. Lead did chemistry. But now guys, watch this. Watch the nitrates. Where did nitrate start? Dissolved in water. Where did the nitrate end up? Dissolved in water. Guys, nitrate did not do any chemistry. There's a name for that. Do this with me. Nitrate didn't do any chemistry. It is what is called a spectator. Now guys, you ready for a really deep thought? Think about this. Let me say it again. Nitrate did not do any chemistry. It started dissolved. It ended up dissolved. But guys, guess what? Nitrate is always a spectator. Why? Because it's always soluble. Guys, nitrate will never do chemistry in aqueous solution. It is always a spectator. Now guys, what about this? Now let's look at potassium. Where did potassium start out? Dissolved in water. Where did it end up? Dissolved in water. Potassium is also a spectator. Think about what that word means. If you're a spectator at a game, are you in the game? You're watching. So are nitrate and potassium. They're just watching everybody else do chemistry. That's where the name comes from. So guys, what about iodide? Where did iodide start out? Dissolved in water. Where did it end up? Piled at the bottom with lead. So did iodine get in on the game? Oh yeah, iodide did some chemistry. And then guys, obviously the lead iodide did because it wasn't there before. So now what we're going to do is we are only going to write down the substances that did chemistry. So do this with me. Lead 2+ did chemistry. The nitrate and the potassium did not. 2 iodides did chemistry. And they came together to form PbI2. Guys, this, I forget that underneath the corner of this, there's a tab. So guys, this is what is called a net ionic equation. And here's the deal. For the rest of the year, this is how we will represent aqueous chemistry. Why do we not care about the nitrate and the potassium? They're spectators. They don't count. They're not doing anything. So guys, when we represent aqueous reactions in this class and for the rest of your academic career, all we care about is the dudes that are doing stuff. And so when we represent aqueous chemistry, we will always write what are called net ionic equations. So again, guys, and these are words that you don't necessarily need to know. This is called the complete molecular. This is called the complete ionic. And this is called, I hate that thing. And this guy is called the net ionic equation. Now, you're going, wait a minute. Wow, this is a big process. If I've got to write the complete before the net, or the complete molecular before the complete ionic, before the net ionic. Guys, quickly you're going to learn to write these without doing the others. But for now, if you need to write all three, you can do that. But quickly you're going to learn to just work these through in your head. So guys, we're going to have some homework today about writing net ionic equations. So we're done. Go ahead, Ronnie. What's up? Please. Say that again. You lost me. The only thing I'm questioning is the cause and effect in your thinking. So, if I may, how do we know that this breaks apart into pieces? It's a strong electrolyte. Nitrates always dissolve. How do we know this broke apart into pieces? Because it's a halogen salt that isn't silver, lead, or mercury. That always breaks apart into pieces. Is that what you were thinking? Yeah. So regardless of what the specific reactants are, in a precipitation reaction, you'll always have that double trading of partners. Yeah, Chandler. That's it. Yeah, that's a really cool observation, Chandler. Let me say that back and then let's talk about it. I like the way you're distilling this because you're going, basically all we're doing is writing the reaction for the precipitate. And the answer is yes. The reason is because that's the only chemistry that's taking place. Because remember, a chemical change creates a new substance. And the new substance in these that will always be created is the precipitate. So you're exactly right. Yep. What do you think, y'all? Are we okay? Go ahead, Annika. That's all right. Oh, yeah. It's actually a weird form of a single displacement reaction. Yeah, absolutely. Definitely. Yeah. I can't think right off the top of my head of a real-world example, but yeah, no question. Yep. You guys okay? So, guys, amazingly, and again, I don't mean to sound condemning, but all of this stuff that we've just gone over in 2 full days normally takes 1. Isn't that crazy? And again, I only mention that to say, you guys don't really have a sense of, again, and I'm not calling you handicapped, but how far removed we've been from this material for so long. And guys, the only reason that I mention this is because if you find yourself in the middle of this going, what the crap? This just feels so distant and so foreign, and wow. Because understand, as a group, we are all in that position, and it's not your fault. Trust me, I'm behind you all the way. And guys, we're going to get through this. But really, just, you guys are, 2 days to do what normally takes one. We're all in this boat together, and it's going to be fine. So, guys, with that said, this is going to freak out. Yep, let's go again. Clear this. And so, guys, in our notes, there are definitions of completed molecular equations, spectator ions, and net ionic equations. You don't need to know them, but they're there if you want them. Again, here is our homework. We'll pick up the ones that we couldn't do previously. And, guys, we're not going to have time to do our GroupMe group. We'll catch it after the weekend. So, guys, we're going to take a break. We're doing the rest of them. Yep. So, guys, we'll take a break there, and we'll go into lab when we get back.